Hello, welcome to this video. This is 1-8 and we're going to talk about the intermediate value theorem in calculus. The intermediate value theorem, one of the three existence theorems that helps prove that a certain value exists. So let's go ahead and talk about the intermediate value theorem. Alright, just a general question here. Suppose that you were 4'6" tall when you were 10 years old. And I'll go ahead and highlight this just to kind of help illustrate the connection here. You were 4'6" when you were 10. Now you are 5'7", okay? And keep in mind, now you're probably older than 10, right? If you're watching this video, you're probably 16, 17, maybe 18. Okay, was there a time when you must have been exactly 5 foot tall? When would that time have occurred? I mean, yes, in order to get to 5'7", you had to be at least 5 feet tall. Okay, and when would that time have occurred? Well, it would have had to occur sometime between when you were 10 and now. That is the concept, and that's the idea behind the intermediate value theorem. It's kind of like a duh, like it exists, and we go ahead and illustrate this with a couple of conditions, okay? So let's go ahead and introduce you to the intermediate value theorem. Commonly abbreviated as IVT, the intermediate value theorem. If f is continuous on the closed interval a to b, where f of a and f of b are not equal, and k is a number between f of a and f of b, then there is at least one number c in the interval, the closed interval a to b, such that when I plug c into the function, it gives me k. And you may be saying, like, what? Like, that doesn't make any sense. So let's go ahead, let's draw a picture which will help us make sense of this. So I have an axis here. I'm going to go ahead and say this is our x-axis. This is our y-axis, or our f of x values. And what I'm going to do is I'm going to plug in the variables that they said. They said, okay, a and b. 2 points in time, right? This is like when you were 10, that's a, and now, which is b. Okay, and then we have 2 points. I have a point here at a. This is you being 4'6", and I'm going to call this f of a. That's the first y value. And then I have a point up here for b. I wanted that to be blue. Here's b, and let's call this f of b, right? So 2 x values, when you plug them into a function, they spit out 2 y values. Okay, the IVT uses these values, and it says, okay, if there exists a k value, which is somewhere right here, there must be a c value somewhere in between a and b that gives us k. So f of c is k, and I'll plug this in here. This is f of c. Okay? Now, again, the reason that this works is because our function has to be continuous. Like, it has to be connected. Okay? If it's not continuous, all bets are off. And then 2, if our k value there is not between f of a and f of b, then that bet is off too, okay? Can't talk about it. Alright, so let's go ahead and talk about some things. Intermediate, this just means in the middle. You could say in between, it's all the same thing. Intermediate, in the middle. Now the IVT is showing a point exists between 2 values, in the middle, and that's the way you need to think about it. Some important notes about the IVT. IVT is called an existence theorem because we're showing that something exists. We will learn 3 of these in calculus. More to come. Now, when using the theorem, we must show that the conditions are met. In order to use this awesome tool that I am showing you, you have to go ahead and show that you can use it. Now, the way I equate this is I think about Thor, and he's not by any means, my favorite Avenger at all, but I just think about Thor. In order for Thor to call his hammer Mjolnir, right? He has to be what? There has to be a condition met, and he has to be worthy. Thor must be worthy in order to get and to summon his hammer, okay? So we have to, in order to satisfy the conditions in order to use the IVT. So what are the conditions? Well, first of all, I told you that the function must be continuous. That is condition number one. Whew! Tripping up over all these C words. Condition number two, the y value we want to guarantee must be between the y values at the endpoints. Now, AP problems rarely or never explicitly ask you about the IVT. You have to recognize it. You have to interpret this. They'll say something like, must there be a value? Or can you guarantee a value? Or show that there must be a value? Or does a value exist? They use these phrases, and that's our recognition that this is an intermediate value theorem process, okay? All right, so we're going to go ahead and we are going to talk about the steps applying the IVT. The first one, which is not number one here. Step number one, what I want you to do is make sure that the function is continuous. Make sure that the function is continuous on the closed interval. Step number two, which is not step number two on here, you need to go ahead and find the endpoints of the given interval by plugging values into the given function. And we'll see that in a second. And then subsequently, condition number three, which is here, show that the requested y value is between the two y values at the endpoints of the interval. Okay, step one, step two, step three. Then, step four, you go ahead and invoke the IVT by using the following condition. Since f of x is continuous on the interval, they'll give you the interval. For our sakes and purposes here, you can plug in the closed interval of a comma b. The IVT guarantees that, and I'm not going to search to formulate this sentence or try to word something together that sounds good. I'm just going to regurgitate whatever their question was. There you go, right? We'll go ahead and say that. So I'll show you an application of this here in a moment, but I want to talk about some situations, just seeing, can I use the IVT? I just want to analyze the conditions first to get you familiar with them. So here is example number one, and it says, does the intermediate value theorem guarantee a C value on the given interval? So here is A, and my function f of x is x squared minus x. Well, this is a polynomial, and polynomials are continuous everywhere, always continuous. Okay, so condition number one, I can say f of x is continuous. Condition number two, does my k value, which here's f of c equals 12, okay, here's my k value, does it live between the y values of a and b? Okay, f of a and f of b. So here's what we have to do. This is step two. What are your endpoints? So I'm going to say, okay, what's f of 0? I plug this into my function. 0 squared minus 0, that is 0. Okay, what's f of 5? 5 squared minus 5, this gives us 20. So does my k value live between f of a and f of b? Well, the answer is yes, it does, right? F of 0 is less than 0, which is less than f of 5, right? And if you want to substitute these values, not 0, 12, that's our k value. If you want to substitute these values in, you can go ahead and do that. Here's 20. So yes, IVT applies, and we'll talk about our conclusion in a moment. But those are your two conditions, and when everything is peachy. Most of the time on the AP test, it's peachy. You just have to show those two conditions. All right, let's look at some non-examples. g of x is equal to x squared minus 4 over x minus 2. Well, this is a rational function, and if I factor this top and bottom, x minus 2, x plus 2, we can see that I have a factor that cancels. And when I have a factor that cancels, that is a whole or a discontinuity. Really, I don't have to factor that and cancel to show that there's a discontinuity. Right away, you can see there's a discontinuity. Now, with rational functions, it's either going to be a whole or an asymptote. But for our sakes and purposes, there's a discontinuity. Now, where is that discontinuity? Positive 2. Now that is smack dab in the middle of our interval. So g is not continuous on that interval 0 to 3. Guess what? G is not continuous on 0 to 3. IVT does not apply. Mr. Schwarberg, what if our interval was 2 to 5? Well, isn't 2 still part of this interval? It's closed. That means I include the endpoints. So even if the discontinuity occurs at the endpoint, guess what? No, you cannot use it. I'll say no. Mr. Schwarberg, what about 3 to 6? Or 3 to 5? 3 to any number. Well, now is 2 on that interval? No. So then that condition is met. Okay, very good. All right. Next example. C. I don't know what's up with my paper. This shouldn't be there for you. Hopefully by this time I will have corrected that. And it should just say h of x. All right, I have a piecewise function. H of x is equal to x for all x values less than or equal to 1. 3 for all x values greater than or equal to 1. Okay, so does the IVT apply here? Well, I got to go ahead and I got to check continuity. Okay, so what is the limit as x approaches 1 from the left of h of x? It's piecewise, so I'm going to inspect the cut points. I want to make sure this piece, the top piece, is equal to the bottom piece. So my limit from my left, that's just going to be 1, right? If I plug in 1. Okay, what is the limit as x approaches 1 from the right of h of x? That's 3. Oh, this is a jump. Discontinuity. So I say h is not continuous. IVT does not apply. Okay, so those are the cases where we just have to check the conditions, okay? Now, another thing too, one of my students said, hey, Schwarberg, what if, instead of 3, what if this value was 1? What if it was continuous? What if they matched? Okay, so condition number 1 is met. So then condition number 2 would be, here's A, here's B, I gotta find my endpoints. What's h of 0? Well, I plug it into my top piece, my output would be 0. Then h of 4, I plug that into my bottom piece, which is just 1. It's always a constant function of 1. I don't get 4, I get 1. And then we say, okay, is k between those? Here's h of 0, which is 0. Here's h of 4, right, which is 1. And our k value is 6. Is 6 between 0 and 1? No. No. So then condition number 2 fails. So that's an example of what condition number 2 looks like. Okay, let's go ahead and let's look at an example. Okay, here's the first example. Example number 1. The function f of x is continuous with selected values of f of x shown in the table above. Is there a value c with 1 less than c less than 7 such that f of c is equal to 0? Justify your answer. Here's your clue that we're using the IVT. Is there a value c? Okay, so what I got to do first, I got to check my conditions. Is the function continuous? Well, don't they tell us f of x is continuous? So therefore, boom, Condition number 1. Condition number 2, I need to go ahead and find my endpoints. So what's f of 1? Well, my y value is -2. The interval closes at 7, okay, f of 7, that's 6. All right, and my k value is 0. So doesn't doesn't 0 live between f of 1 and f of 7? It does. It does. So I state that, I write that. And then we go ahead and write our result here, or our conclusion. So we say, so since f of x is continuous and 0 is between f of 1 and f of 7, so the IVT guarantees a C value. And here I'm just going to copy with what they said. A C value with 1 is less than C, which is less than 7, such that f of C is equal to 0. Okay? All right. Here we go. Example number 2. Okay, we're going to go ahead and use the intermediate value theorem to show that g of x has a 0 in the interval 0 to 1. Now, this example is different because they give us a function. I have g of x, and then the k value that they give us is 0. They don't explicitly say that, right? And we want that x to be in the window 0 to 1. So we're going to go ahead and we're going to check our conditions. So condition number 1, I have to show that the function is continuous. Well, again, here g is a polynomial. G is continuous. Polynomials are continuous everywhere. So we can say g is continuous. Number 2, now I need to go ahead and check the y values. So what is g of 0? Okay, when I plug in 0 cubed plus 2 times 0, well, that's 0. Minus 1, we get -1. Check the other endpoint. What is g of 1? 1 cubed plus 2 times 1 minus 1. That gives us 2. So I'm going to take these two values, -1 and 2, and I need to show that my k value is in between them. What's our k value? Has a 0. Okay, I want that y value to be 0. So yes, it does work. So the two conditions are met, and then I'm going to go ahead and provide a statement. So again, since g is continuous and 0 is between 0 and 1. No. I was thinking about something else. Between g of 0 and g of 1, the IVT guarantees. Mr. Schwarberg, I don't know what to write. Okay, the IVT guarantees, and then just copy to show that g has a 0 in the interval 0 to 1. So we say that. Guarantees that g has a 0 in the interval 0 to 1. I copy it. Verbatim. I plagiarize it. I did it. Writing my conclusion. There we go. Okay, example number 3. Oh, this is where the fun begins. Example number 3. The functions h of x and k of x are continuous. Hey, telling us continuity. Thank you. They're so kind. Selected values for h and k are shown in the table below. Okay, there's a table of information. Next prompt. Let m be the function which is equal to k of h of x. Okay, that's composition, right? H of x here is embedded in k of x. It's embedded in k of x. So they defined a new function. Can you guarantee a value c where 1 is less than c, which is less than 9, such that m of c is equal to 4? Give a reason for your answer. Okay, so this is IVT, again, based upon the wording here. Can you guarantee a value c? And then usually the interval gives it away, and then this m of c equals 4. So really, for quick identification, I need to go ahead and identify continuity. Number 1, is m, right, that's the function I need to use, is m continuous? Well, you may have not learned this, but functions that are continuous, such as h and k, if I have a composition of them, if they're both continuous, then the composition is also continuous, okay? And I'll just go ahead and write that here. This is more for you. So since h of x and k of x are continuous, m of x, which is k of h of x, is also continuous. Okay, there's condition number 1. Condition number 2, I now need to evaluate the endpoints. So I want m of, and I'm going to check my interval here. So here's a, here's the starting point, 1. So what's m of 1? I'm going to go ahead and plug that in. So this is k of h of 1. Okay, and I'm going to do inside out when I'm evaluating. So I start with h of 1. What's h of 1? Well, on my x value, I'm going to find 1. And then here's h. Here's h. So h of 1 is equal to 5. Okay, so this is equal to k of, and I'm going to plug in 5 here. And then now I need to go ahead and find out, okay, what is k of 5? So I go to my x value 5, and I look at k, 7. So this is equal to 7. That's how evaluating compositions work. Okay, now I'm going to check the second endpoint, 9. Here's the b value, m of 9. So this is k of h of 9. So h of 9, that's going to be 2. So k of 2. Now I look at 2 and I evaluate k, which is 1. There you go. So I ask myself, okay, is my k value, and again, k here they want to be 4. M of c is equal to 4. They want k to be 4. Is 4 live between 7 and 1? Yes. And I'm just going to state that. Make sure you state that. 1 is less than 4, which is less than 7. If you want, you can add this in. This is m of 9. This is m of 1. So I'm just stating that condition. I'm showing that 4 is between those endpoints, between those y values. All right, and now I just go ahead and state my conclusion. So I say, since m of x is continuous, on 1 to 9, and 4 is between m of 1 and m of 9, the IVT guarantees what? What did they want? A value c, where c is between 1 and 9, such that m of c equals 4. There's your conclusion. All right, hey, that is the intermediate value theorem. That is the intermediate value theorem, okay? All right, I hope you learned, first of all, what the intermediate value theorem stands for. 2, I hope you learned the conditions of the intermediate value theorem. 1, that the function must be continuous on the closed interval. 2, that the k value that they want you to show, where there's a c value that's equal to that, the k value must live between the two y values, okay? All right, I'll catch you in the next video. Have a good one. See you next time. Give me a thumbs up, like, subscribe for some more awesome math video-ness. See ya.